All right, here's a follow-up to the first lesson on exponential growth. In the last video, we made some observations, and what we learned is if a function, well, first of all, if a function is in the form of a times b to the x, that's an example of what's called exponential growth, and the variable here is an exponent. And I wanted to draw a comparison to linear functions, which we studied before, which can be written in the form a plus b to the b times x. And here we're going to keep adding b over and over and over again. And here we're going to keep multiplying b over and over again. But both of these functions show starting at a, and so a is your starting value, and then the b has something to do with the rate of increase. This is the slope or rate of change. This isn't exactly the slope or rate of change, but it is, in fact, what we call the growth factor. That's the number that's going to be multiplied over and over and over again, hence the word factor. And because it's growing, the function values rather, then we call it a growth factor. So if we take what we learned about linear functions and apply it to what we're doing with exponential functions, we can see the only major difference is we're adding repeatedly the same b value over and over to a, and here we are multiplying the same b value over and over again to a. So that can be applied then in semi-real life situations. Like population growth and investment growth are really common examples of this. So if there was a town that had a growing population, there were 30,000 people in the town in 2005, and they measure a 5% annual growth rate in the population. Then it says make a table which would show the next 5 years worth of growth, and then see if we can find an equation to model that growth. Now these are the calculations that I came up with, and in the process I multiplied 30,000 by 5%, and I got 1,500. That's not next year's population, that's the additional population, so I added that to 30,000. But so the problem that came up when gathering these data was that the method that I used for calculating the data was as follows. I would take the initial $30,000 and then I would add to it 5% people, not dollars. I would add to it 5% of that population added to the initial population, and that's how I got my figures. But the problem is I want this to look like an exponential growth function, and this does not show a times b to the x. There's this addition in here. So it requires a little bit of algebra. So here's the newer concept. We've seen factoring before, but you see 30,000 and 5% of 30,000 both share the common factor of 30,000. So I'm going to take that 30,000 out of the sum expression, and 30,000 divided by 30,000 is 1, and 30,000 times 0.005 divided by 30,000 is 0.05. So if we add those two numbers together, we get 1.05, which can represent 105%. This makes sense to me now because I can see that what we're going to do is we can multiply the 30,000 times 105%, which would account for 100% of the existing population plus 5% more people. And we can do it all in A times B format. To see the second year then, I'm going to take the 30,000 times 1.05, 105%. That'll give me the first year's population. And then I'm going to take the first year's population and multiply by 105% more, which gives me the second year's population. But when I look at 30,000 times 1.05 times 1.05, I recognize the shorthand. I can make it 30,000 times 1.05 squared. Then in the third year, I'm going to take that population, multiply by another 1.05. So there's a total of 3 1.05s, or 105%, being multiplied by the 30,000. Which means no matter what year I'm in, all I have to do is account for that many 105%, multiply the result by the 30,000, and that'll give me my newest population for any number of years. And I can even go back in time here. I'll talk about that a little later. What I mean by going back in time, though, is we look at make an observation about this particular table, and this is the table representing some solutions to f of x equals 2 to the x, because I know that 2 to the 1 power is 2, and I also know that 2 to the second power is 4, and 2 to the third power is 8. But I'm a little concerned here because I should be able to put in values for 0, -1, and -2, and I'm trying to figure out how to make it work. So what is 2 to the -1 power, and what is 2 to the -2 power, and how do I understand why those values exist? Not to mention, what's 2 to the 0? Well, when I observe the table, I can recognize that going forward, every time I increase the x by 1, I'm going to double or multiply by 2 the y value. So 2 times 2 is 4, 2 times 4 is 8, the next one will be 16, the next one will be 32. I keep doubling. In that case, then, if I was to go backwards, 8 divided by 2 is 4, 4 divided by 2 is 2, so I should probably follow the pattern and go 2 divided by 2 is 1. And then 1 divided by 2 is a half, and a half divided by 2 is 1/4. So that means that 2 to the negative 2 power is equal to 1/4. 1/4 is actually 1 over 2 squared. So I can learn that 1/4 can be represented as 1 over 2 to the second power, and 2 to the second power apparently, when I divide it into 1, it can be expressed as 2 to the negative 2 power. So this negative means instead of multiply 2 by itself twice, it means take 1 and divide it by 2 twice to give me a quarter. It follows then that 2 to the negative third power would be 1/8, because we're going to have 1 over 2 cubed, or 1/8. That would explain then why when I put in my calculator or computer graph of y equals 2 to the x power, I get that exponential growth that we studied before on the right-hand side. But I'm getting asymptotic behavior on the left-hand side, because we get 1/2, 1/4, 1/8, 1/16, 1/32. We get closer and closer to 0, but we'll never actually reach it. So there again we see this exponential behavior of slow, 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 and then suddenly, holy cow. So that's exponential growth in a nutshell. So just so we can understand how the patterns work, if we saw a table of values like this that represent exponential growth, we can observe exponential growth by noticing that 10 times 2 equals 20, 20 times 2 equals 40, 40 times 2 equals 80. In other words, each of the y values is doubling its preceding y value. To get the equation then, I recognize first that the starting value is at 10. So that gives me the starting value for my equation, and then I see that I'm doubling, and that's my growth factor, and I can put that in there for 2, so that's how I get the equation. But what about when I have a table like this one, where I'm not starting at 0, I'm starting at 2, and going upwards? Well, we recognize the nature of 18 and 54. 54 is 3 times 18, 162 is 3 times 54, and 486 is 3 times 162. So we can see the common growth factor of 3 right here, but how did I get the number 2? Simply using that reverse pattern, that if we go backwards in the table, we're going to divide by 3 to get the previous value, and that's 6, and divide by 3 one more time to get to 2. Which means f of 0 equals 2. That means 3 to the 0 power has to equal 1. 1 times 2 is 2. So that's again how I make sense of the 0 power. It must equal 1, because that's the only way it fits this pattern. So if we can generalize this, then we see a function here which is starting with, let's say, $4 and then tripling every day. Again, a very lucrative proposition. And for starters, I noticed that the a value is 4, which puts me at a point here at 0, 4. And then I'm tripling that, so that to get the next point in the graph, all I have to do is triple 4, which is 12. So I have 1/12. Working backwards, if x was -1, I would not multiply by 3, but rather divide by 3. So we have our third point, which is -1 4/3. And all I have to do then is recognize the asymptotic behavior on the right and the ballistic behavior on the left, actually on the right, and then this is the left. I'm still learning my right from left. And there's the exponential growth curve that models this function. Using similar reasoning, when x is 0, we're going to have 1 times a half, so we could start here at 1/2. And then we're going to double that. So double a half is 1, and double 1 is 2, and double 2 is 4. So we get the next 3 points just by doubling the previous. And then I can do the same in reverse. Then I'm going to take half of a half, which would give me a quarter, and half of a quarter is an eighth, and so on. So we can see the curve would look like this, and we see generally exponential growth curves have the same nature. It's just a matter of how long does it take before that spike happens. We can slow it down a little bit by making the b value smaller, and we can slow it down a teensy bit by starting at a smaller number. That enables us then to generalize certain kinds of expressions with exponents that are unusual, like 3 to the -2 is actually 1 over 3 squared, which is 1/9. 4 to the 0 is really just a fancy way to write the number 1, and 6 to the -1 is really just 1/6. So that concludes this summary. Yeah, good luck.